Hello, everyone. Good morning. This is Professor Grenfell's Math 12 Statistics class, and today we're going to explore the initial portion of Chapter 2 on organizing data. Now, just to review, in Chapter 1, we talked about different methods of collecting data, different types of data, what variables are, and so on and so forth. And now, here is an example of some data. And as you can see, this is a big, giant sea of numbers. They've gone ahead and organized it at least into columns for us. But other than that, this data is still very unorganized. It's very difficult to look at and get an idea of what is even going on here. And so that obviously is the motivation for developing different types of organization for our data. We're going to go into a few of those in just a moment. Now, one method of organizing our data is illustrated here below. Uh-oh, I chopped it off. So what we will do is we'll draw an x-axis, and here are the different data values that we will have. So our data points, our datum run from 27 for the lowest value all the way up to 92 for the highest value. And what we can do is just go through one by one, take each piece of data. So 45 is the initial datum or piece of data. And so we would find where that is on our x-axis, and we put a little dot there. Going back up, we see 92. That was one of the values, so we would have a dot above that, and so on and so forth. So the next value is 27, and just go ahead and determine how many times each different value occurs. And so if we have multiple repeats of the value 45, we would go ahead and put how many occurrences of that piece of data we have as just little dots above that. And that would be called a dot plot. If we continued and we completed the dot plot for this data set, notice there's 10 in each column and 5 columns. So we have 50 datum. We have 50 pieces of data. And that would end up producing 50 little dots all throughout here. Now, that is a little bit inefficient. And so what we're going to do is we're going to be considering what are called grouped frequency distributions. And in addition to that, we're going to extend that concept and talk about the histogram for the grouped frequency distribution. So here we're going to be looking at example 2-2. And I managed to capture the data here, but I didn't capture all of the instructions for this example. So you can please find this in your book on page 47. I'll just kind of quickly read through what the scenario is. It says these are pertaining to record high temperatures. These data represent the record high temperatures in degrees Fahrenheit for each of the 50 states. Construct a group frequency distribution for the data using 70 classes. Now, this little sketch here is essentially the general idea of what we mean by group frequency distribution. Here, instead of having a little dot for each individual data value in here, we're going to just say every value that falls into this range, we're going to just count the number of times this occurs. So we don't really care about each individual value and how many dots it has above it. All we're doing is we're counting the number of data values, so the number of dots, if we made a dot plot, that would be occurring in this region here. So we might have some that have a lot of values, some that don't have any values, and then others that, well, I'm sorry, there's no other option. Some that have a lot and some that don't have many, but altogether we're going to count how many occurrences we have in each of these what are called classes. So we're taking the whole interval at which all of the data is spread out across. So all of the data lives in this range here. We're going to be breaking this up into intervals that are all uniform in width. That means they're all the same width. And we are essentially, in this one, we're told we want to have 7 classes. But in general, the rule of thumb is in between 5 and 20 classes. And it's kind of like our choice. If nobody comes and says, here's how many classes you need to have, then we get to kind of choose based on what our purposes are. How much accuracy we want, then we might include more classes. If we want more speed but less precision, less classes. So here they've told us 7. Now, the first thing that we need to do is we need to determine where our data is situated and how far spread apart it is in order to determine how wide each one of these buckets should be. So that's kind of another explanation for this. We have set up these 7 buckets across where all of the data is, and they're all equal in width, and we're just essentially the frequency, that is the number of times that something occurs. We're going to be looking for the number of times that our data point is in one of these buckets. So for example, if our data points are in here, we're going to just count for each value that's in between this range and this range. So let's get into this example. So the first thing that we're going to be doing is determining, like I said, where the data is. If we had to graph it on the x-axis, where would we be graphing? And so what I've gone here is I've gone in and found the highest value and then the lowest value. The lowest value was 100. There it is. Found it. So we have the high value of 134, the low value of 100. The range, that's what R is the highest value minus the lowest value. So it's 134 minus 100 gives us 34 exact. So this gives us a picture of where the data is located, and then the range tells us how far spread apart the data is. And now using this and the number of classes that we have already determined for ourselves that we want to use, this will allow us to calculate how wide each of these classes needs to be. So the class width is going to be defined as follows. The class width, class width is R, that is the range, divided by the number of classes that we want our group frequency distribution to have. So for our particular case, we have 34 for the range. We wanted to use, they told us to use 7 classes. And so what this works out as is approximately 4.9. Okay? And now here, we've got to pay attention. We're not going to round. So if I say we round it, that's technically incorrect. I'm going to say we bump it, because no matter what this number is, we're always going to bump it up to the next highest whole number. So it's going to be too tedious to make the class width 4.9. All of our data is measured in whole number degrees. And so we're just going to say our class width is 5.0, right? Even if the number of classes divided into the range a whole number of times, we would still bump it up. So even if we did this division, let's suppose it was 35 divided by 7, that would go in exactly 5.0 times, but we would still have to bump this up to the next highest whole number. So even if it goes in a whole number of times, you still add 1 to that for the class width. So there will be other times where we have to follow different sorts of rounding rules. So again, this is not rounding in the traditional sense. This, gotta try to call it something different. We're going to bump it up. So I'm going to call it bumping instead of rounding. I don't know if that's a real, actually, precise term. So a frequency distribution is going to consist of essentially, well, these 4 columns, but the main important ones are the class limits and then the frequency. So the class limits are going to describe the class itself, how wide it is, where it starts and where it finishes. The boundaries are going to be the technical start and end points. And remember, these are going to be similar. These are exactly the same as the boundary of a number that we discussed in chapter 1. The count, or in the book it says tally, is we're just going to go through our data and count the total number of values that fall into each one of these classes. And then after we've tabulated that, we'll just put this as a number right here for the total number of occurrences of data within this range, the class limit over here. So what we're going to be doing is starting with the lowest value. We've got 100, right? The class limits are a little bit different. These are not actually going to touch. The class boundaries are bordering on one another. So they're not actually going to overlap, but the upper and lower are going to be the same for consecutive classes. Now, the class limit starting with 100, we want the width of this class to be exactly 5, but we don't want it to overlap with the other class. So we have 100 as the lower limit for our first class. The class width is 5, so we're going to add 5 to 100. That gives us 105, and that will be the lower limit for the next class, all right? And now here, since our class width is 5, which is a nice easy number, we can just go ahead and extend this, extrapolate, and continue writing in our lower limits, okay? And we should have a total of 7 values here. So we have 1, 2, 3, 4, 5. Okay, so 125, 30, and let's see, I think that is 7 values. 1, 2, 3, 4, 5, 6, 7. Yes, perfect. All right, now the upper limits, a little bit more difficult for me to think about it. They're not hard, just they kind of trick me sometimes. So here's what I always do. I always determine the lower limits first. Normally I would have to edit this out, but this was too funny. I was interrupted just now by my wife screaming that my daughter had a lizard in her hair, and it was indeed true. Anyway, okay, so let's back up. So I have filled in all of the lower limits for each one of these classes. We don't want these classes to overlap. So therefore, if I have a data value of 104 and a data value of 105, I don't want there to be 2 different classes that this same data value can go into. So I better not have this upper limit for this class be 105. That would be bounding on this one. They would be overlapping. So if I had the value 105, would it go in this class here, or would it go in this class here? We don't know. There's no way of saying. So in order to kind of make sure that this works, right, what we're going to have to do is just decrease it by 1. That's why, for me, it's easier to do it this way. Fill in all of the lower limits, and then just backtrack to find the upper limit. I just take this value here, -1, and put it right there. Okay, 110 minus 1 is 109. Okay, -1, we get 114, and so on and so forth. And so that's this way we don't have any overlap. There's no ambiguity about which class to put this into. So notice here, our class width was perfect in order to encapsulate all of the data values from the lowest all the way up to the highest. And that is essentially why we had to increase the class width. Instead of rounding it, we had to bump it. If we didn't, even if it were a whole number, if we used up all of the number of classes that we needed, we would have that last value, that highest value, would not have a class to go into. So let's go over this, just because it's a little bit important. The boundaries for these classes are going to consist of the lower boundary for the lower limit, and then the upper boundary of the upper limit. And that will tell us, okay, those are the actual ranges of data values for the buckets or the classes that they're going to fit into. So here, this is technically from 99.5 all the way up to, but not including 104.5. So that's the lower limit for that's the lower boundary for the lower limit, and that is the upper boundary for the upper limit. And the nice thing about this is these values are going to be exactly the same. Okay, so 104.5, technically we don't include that last part, and so this one is going to start right at 104.5. This is everything up to, but not including that value, and so this one just picks up right where that one left off. It's going to go to 109.5. This is not subtraction, by the way. This is just saying that the spread or the span of this. This is going to go 109.5. That was easy because we just had that right there. All the way up to 114.5, and so on and so forth. So I've just gone ahead and filled those in. So notice the class limits or the class boundaries are essentially equivalent to one another. So if I have the value 105, it is for sure going to only go in this class. And looking at the boundaries, you can tell it's not going to go in here because it's certainly greater than 104.5. 105 itself would fall into this class here. So notice the boundaries are kind of there to just make sure that we don't overlook any of the values. All right, and continuing on, here is where we're going. We're going to go ahead and look at each one of these limits. So this first one from 100 to 104, I'm going to go back through my data and just put a little tally mark for every occurrence of data that is in this range. So in the second column, we have a lowest value of 100. And other than that, the second to last column, we have the value exactly 104. There's no other data values that are 100, 101, 102, 103, or 104. So we've just got a count of 2 here. So our frequency for the first class would be 2. 2 occurrences of data values somewhere, anywhere, in between 100 and 105, right? So we're basically just saying, okay, look, all of this data from 100, 101, 102, 103, 104, all of those are, those are technically separate data values, but we're just going to count total number that are in that range. So all of the values that are close enough to 100, 104, 102 would be the midpoint of that class. There's 2 total, all right? Next, we're going to go ahead and do the same thing for the next one of these classes here. So we go through every time we see a data value in this column, we're going to just go ahead and put a tally mark. So I'm finding them, and I found a total of 8 values there. Hopefully I counted that right. And so here I've just gone through and filled the rest of this in. Notice I didn't bother making tally marks for all 18 of these. I just kind of kept track of it on a separate sheet of paper. And then the last thing, all of these frequencies, if we add up all of the frequencies, well, what are the frequencies? The frequencies are a measurement or a count of the total number of data values that are in a certain range. And here, if we add up all of the data values that we've looked at that are in the whole range for the whole extent of all of these classes, what should that be? Well, that better be the total number of data values that we started with. Otherwise, we double counted or we skipped one or some. Okay, so here, the bottom line for frequency distribution is it is a method of organizing and sort of compartmentalizing our data. If we have the raw data, that is everything. That is the complete description of our data set. However, when you're looking at raw data, it essentially looks like just a giant sea of a whole bunch of numbers. And it's very easy to kind of get confounded by what are all of these numbers. And so what we have done here is basically just said, okay, look, we have all of this data set. There's a whole giant ocean of data. And what we're going to do is we're going to just set out a series of buckets. And we're going to let all of the data fall into all of the various buckets. And then we're just going to see how full are each one of these buckets. So here I've got the range of 100 to 104. That's the first bucket, and only 2 drops fell into it, and so on. All right. Next, well, the last thing that we're going to be speaking on in this section is what is called a cumulative frequency distribution. So the cumulative frequency means the set of all data values that are less than a certain amount. So notice this is our lower boundary for that first class. So our data values are all 100 and above. 100 is the lowest value. So there is nothing that is less than 99.5 degrees. No high temperatures, no record high temperatures, less than 99.5. And how many are there that are less than 104.5? Well, that would be the total of how many are less than 99.5 plus how many there are in between 99.5 and 104.5. So that would be simply 2. And backing up, just to take a look at this, essentially, well, let's go on to the next one before we back up. Gotta have something to back up to, right? We think about how many are there that are less than 109.5. We could go to our original data set and count them all up, but if we've already constructed a frequency distribution, a grouped frequency distribution, we can simply say, okay, look, there were 0 less than 99.5. There were 2 that were less than 104.5. Okay, in between 104.5 and 109.5, there were exactly 8 in there, because that's what it says right here for this class, from 104.5 to 109.5. And so if we have 0 so far and added another 2, and then there's 8 in between 109 and 104, then we're going to just say there's a total of 10 there. And going on and so forth, we would simply just take each one of these frequencies that are occurring from our grouped frequency distribution, and to get the very first value, well, we start with 0. To get the next value after that, I'm just going to say that's 2, right? Where I got this 10 from, that came from the 2 plus the 8, right? The next value, what was it? Or what's it going to be? Let's see, 2 plus 8 plus 18. That's where I got this 28 from, right? And just continuing on, we'll add the next value to get the subsequent value for our cumulative frequency. So we'll have plus another 13, 28 plus 13 gave us 41, plus 7 gives us 48, plus another 1 gives us 49, and plus 1 more gives us 50. So for the cumulative frequency, we don't have to total it up because it already is a total. And when we get down to the bottom here, the set of all values that are less than 134.5, well, our highest value was 134. So that means all of the data values are less than 134.5. So this number here, the cumulative frequency for whatever the last class is, that better be equal to the total for your grouped frequency distribution. Okay, I wanted to get into what a histogram was, but we'll pick up with that in the next video. So we'll pause for now, bye for now, and see you on the flip side.